Okay, so as you guys know, the title of this P&S is Hand-on Acceleration on Heterogeneous Computing Systems, or P&S Heterogeneous Systems for short. My name is Juan Gómez Luna, as you know, and I work with Professor Mutlu. This is the description that you can find in the course catalog. For sure you have read it because you joined this P&S. But same as I did in the presentation of the other P&S yesterday, I want to take a look at what are the objectives, because there are some keywords here that it's important to understand to completely comprehend what's the goal of this P&S and what are its contents about. So there is one problem that we need to solve, and this problem is the difficulty of scaling the performance and efficiency of CPUs. This is something that is coming from the last 2 decades at least, and this has affected many important workloads. For example, machine learning and artificial intelligence, but not only these ones, but also bioinformatics, graph processing, medical imaging, personalized medicine, etc. So what do we need to deal with this issue, the difficulty of scaling the performance and the efficiency, which in the end is something that we need to solve, because in some sense the progress of the society these days is based on computers being faster and faster, right? Not only computers, but any other computing device like or laptop or tablets or cell phones, etc. We have the heterogeneous devices coming to the rescue. About 10 years ago, or a little bit more than 10 years ago, graphics processing units turned into general purpose devices, general purpose parallel processors, and they started being used for many different applications, important applications. And as this description here says, they have been critical to enable the recent rise of machine learning and artificial intelligence. And it's not only graphic processing units, it's also, for example, field programmable gate arrays. These are even older devices, but they are more and more important these days because they can provide very good improvements in terms of performance, and especially in terms of energy efficiency. And they are not only they are not the only heterogeneous devices that we are going to talk about in this P&S. There are also specialized accelerators, like for example, neural processing units or tensor processing units that are being used to for training and inference of neural networks, and even more recently, like a very interesting trend that connects these P&S with or other P&S is near data processing architectures, right? So it's like, I would say, like the most recent trend in the availability of heterogeneous devices. But still, even though we have been programming GPUs for more than 10 years, even though there are many researchers, like for example, Behzad and Gagan, who are in the meeting with us, who have a lot of experience with FPGAs, there are still many challenges that we need to tackle. In this P&S, we are going to try to tackle some of these challenges, and one of the places where we are going to start is implementing heterogeneous applications, either using GPUs or FPGAs. But also, there are other important things to take into account, or the important issues to deal with, like, for example, workload characterization and programming tools. What type of tools do we need? What is important, or what's necessary for a particular workload to be more or less suitable for a particular device, and also scheduling and offloading techniques. When is the right time to offload some computation to this accelerator or GPU, FPGA, or whatever it is. Don't hesitate to ask any questions, interrupt me whenever you need it. Even if you type in the chat, I will try to check from time to time whether there are any questions from you. So yeah, please feel free to participate whenever you want. Okay. So as I said, heterogeneity is also, so heterogeneous devices are also nothing new. In reality, they have existed for decades. And one relevant example are the SIMD extensions that conventional CPUs have since at least the 90s. So here, this slide, you may have seen it because it's part of the required materials that I provide to you in my email last week. It's the example of the MMX instruction set, the MMX extensions that were included in the Intel Pentium architecture in the 90s. And they are essentially a SIMD processor. They are essentially a compute unit that allow you to execute multiple instructions to operate with a single instruction on multiple values in parallel. The example that you have in the slide is pretty simple. It's and it applies to image processing. It's the goal here is to do what is called the chroma keying, overlaying an image and a background. And it's a relevant example because these MMX extensions were called multimedia extensions because they were originally devised for multimedia applications. And essentially, this example consists of an image. This is, for example, a show woman appearing in the TV who has at her back a chroma. The color of this chroma is blue, even though you cannot see this in the screen. And what we essentially want to do here is to replace the background, the blue background, with this blossom background. So how would you do this in a sequential CPU? How would you do it with a simple C program? You just need to go one by one over all the elements of the image and check whether this element, this particular pixel, is blue or not. If it's blue, then you replace it with the corresponding pixel in the blossom background. And if it's not, you replace it with the, so you just keep the pixel corresponding to the woman, right? So at this, because in the end, the whole computation that we need to perform here is completely regular, and you need to repeat this short sequence of code for every single pixel in the images. You can do this in parallel, and this is where these SIMD extensions are pretty useful. And here you can see the second slide with a little bit more details about this example. How would you need to operate? What are the instructions that you would need to use? The first thing that you need to do is to create a mask that checks whether, so that helps you check whether the corresponding pixel is blue or not, and then you apply this mask onto the image, and then you obtain the final image that you wanted to get, the woman and the blossom background at the back. Any questions so far? Okay, as I said, this is part of the required material. So if you have any questions about this example or any other contents of the required and the recommended materials, you can use the Moodle forum. You can for sure reach us over email, or you can use the Moodle forum it's available to you in Moodle. We will take a look at the Moodle page in a few minutes. Okay, the thing is, that was just an example of some, let's say, archaic way of heterogeneous system, a conventional CPU, including SIMD extensions, but this has been evolving over the years, over the last 2-3 decades, and we have continued including new devices, new heterogeneous devices into our computing systems. This is just an example of what could be future computing system. And actually, I used to say this like 4 years ago when I created this slide and I created this picture, because by that time we had the vision of incorporating not only CPUs, not only GPUs, but also FPGAs and even more devices into the same chip. And as you can see, I mean, as you will see in a couple of slides, this is actually something that has happened quite recently. And in this pictorial representation of this heterogeneous system, you can find CPU cores with their corresponding cache hierarchy, L1 and shared L2 in this case. You have the GPU with multiple compute units or general or GPU cores. Each of them also has its own L1 or maybe kind of scratched out memory and so on. Even an L2, it's also quite typical in GPUs, as you will also see in the next slide. And then here we have a reconfigurable fabric or an FPGA, and they all are connected in some way. They may even share level of cache, L3 in this case, last level cache, and they may be connected through non-coherent buses and also coherent buses that ensure the cache coherency across the different caches. And this is also kind of a more recent and current trend, because in some way enables and facilitates programming. But yeah, this is something that you will have time to learn, and we will have time to discuss later. Okay, what are the goals of this P&S course? So first of all, we will introduce the need for heterogeneity in current computing systems in order to achieve high performance and energy efficiency. We are already talking about this, why we need heterogeneous devices, essentially because we want to increase the performance and the energy efficiency in computing systems, and we want to use the most suitable device, or if possible, use the most suitable device for every particular workload or part of workload or application. You will get familiar with some of the different heterogeneous devices that are available in current computing systems. We're already talking about CPUs, GPUs, FPGAs, and you will learn about how to program these devices. And to program these devices, you will need to develop your ability as a programmer, but also understand how do you need to distribute the workload and what are the parallelization strategies that you need to use to make use of these heterogeneous devices. In summary, you will work hands-on on programming the heterogeneous architectures, analyzing the workloads that can fit each of the different devices in the heterogeneous architecture, proposing scheduling and offloading mechanisms, and etc. What exactly you will work on is something that we will discuss in our next meeting next Tuesday, where we will present the different project proposals that we have for you. Okay, yeah, let's take a look at some examples, because I'm talking about the heterogeneous devices. I just showed you a pictorial representation of some heterogeneous system, but let's take a look at what we can call state-of-the-art heterogeneous devices. First of all, I started the meeting talking about GPUs, and here we have the most recent and powerful GPU in the market, which is the NVIDIA A100. It was announced like almost a year ago, if I recall correctly. It was in April 2020. It's kind of a beast. It's kind of a supercomputer by itself. And as you can see here, it has 128 GPU cores, which is actually a lot. I think it's they never produce a GPU with so many of these, the way NVIDIA calls them is streaming multiprocessors. We will simply call them GPU cores. And it's not only the large number of GPU cores, but also really interesting to me is the large L2 cache that you can see here in the middle. It's like 40 megabytes in size, which is, I would say it's like at least 4 or 6 times larger than the L2 cache in the previous generation. This is something really important. And why is that? Because in the end, most computing systems these days are bound by the access to the data, the access to memory. So the larger you can have a cache, the better, because the cache is the place where you put the data that you use more frequently, that you reuse more, and the larger this cache, the less frequency you will have to go to the main memory in a CPU or the global memory in a GPU, because that's the way it's called. And by the way, this global memory is HBM2, is a 3D stacking memory that pretty large for a GPU, 40 gigabytes, and also very, very high bandwidth, 1.5 terabytes per second, which is pretty impressive. As you can see, the HBM cubes are represented here on the left and on the right, and there are 6 of them in total. We can take a closer look at the core, at each of these GPU cores, and this is one of them. You see, SM streaming multiprocessor. As you can see, each of these streaming multiprocessors is divided into 4 parts, but in reality, these 4 parts are sharing the same L1 instruction cache, but they also have kind of, they call it L0 instruction cache, where the instructions that are being used are cached, and this somehow represents the whole pipeline of the SM with the warp scheduler, which is the unit that selects the threads that are going to, and the instructions that are going to be fetched from the instruction cache and issued or dispatched onto the ALUs, onto the computing, the functional units, which are these ones that you can see here. There are some of them for integer 32s, or for 4-byte integer operations, or floating point, or double precision as well. And here you can see some figures, right? Like 19.5 teraflops, single precision, 9.7 teraflops in double precision. These 2 numbers are larger than in the previous generation, but in reality not so much large. And actually, if you see the previous generation is the V100, you can find a similar slide in the presentation that I provided to you over email. You will see that these 2 figures here are not so different. They are a little bit bigger, but not too much. But the one that is really much bigger is this one. That is the throughput that you can achieve for floating point 16, for 16-bit floating point computation using the so-called tensor cores, which are this part of the SM that you see here. And what are these tensor cores? In reality, these are just like a multiply accumulate operations that are essentially used for matrix multiplication or for matrix vector multiplication, which are the key primitives that are used for training neural networks or deep neural networks and inference in these deep neural networks. So what NVIDIA essentially did, because GPUs are so much being used, and actually they are the accelerator of reference for training machine learning and neural network workloads, what they did was embedding these specialized cores into each of the GPU cores. Okay, any questions so far? Okay, fine, I can continue. Here, this is another interesting example, and actually it's device that we are starting to work with at this time. Is a Xilinx Versal. It's interesting because it kind of resembles the heterogeneous system that I showed in one of my initial slides. What this Xilinx Versal contains is, inside the same chip, there are 3 different types of devices. They are they are, I mean, they are there because they are good at different workloads. And here you can see some examples. Scalar processing for complex algorithms and decision making. This is what the type of operations that are usually good for a GPU. Then you have adaptable hardware. This is the reconfigurable fabric, the FPGA, and this is usually for processing irregular data structures, for latency critical operations. And then we have the vector processing, similar to a GPU or a SIMD unit, which is pretty good for data level parallelism. And actually, you can take a look in the next slide about, I mean, it's like kind of a little bit more detailed representation of these scalar engines, which in reality are CPUs. And actually, you can see there are two CPUs here, dual core ARM processor A72 and dual core ARM Cortex R5F. And then there we have in the middle the adaptable engines. This is the reconfigurable fabric, and here on the right hand side we have what they have called the intelligent engines, which is kind of vector processor or GPU. Okay, there is a question. How does the chip decide to use which compute engines for each task? Is there an inference profiling mechanism to classify workload? This is a very good question. And the first answer to this is that you will be the one who will decide what's the right place to execute a particular operation, a particular kernel. Why is that? Because you as a programmer will know your workload, you know your program, and you know when you have more parallelism or more regular parallelism or more irregular parallelism, and based on that you will decide whether the CPU is the right place or the FPGA or the GPU is the right place. But as you said, or as you're asking, what would be the interesting thing here would be to develop automatic mechanisms to be able to make these decisions. And these can be done with some, for example, online profiling by observing how a particular workload is running, for example, on the CPU core. Based on how many operations you are repeating, you might be able to identify parallelism. That could be one possibility. Another possibility could be to have some sort of intelligence, some sort of machine learning algorithm that can extract characteristics of the applications and can extract that, and these characteristics may be statically obtained, for example, from the compiler, like for example, the number of instructions, the type of memory accesses, how many times do we access the same data, and these kind of metrics that we can use. They can be, as I said, statically obtained by the compiler, or they can also be obtained dynamically online during the runtime, during the execution. So this is actually a very good question, and it's one of the goals, or one of the challenges that we want to tackle in this P&S. Okay, another example of a heterogeneous device. It's actually something that I presented yesterday, and I also mentioned in the beginning of the meeting, is processing in memory. And this same slide, I used it yesterday. This is a slide from Professor Mutlu's lectures that presents the UPMEM Processing-in-DRAM Engine. This is processing in memory system that essentially consists of multiple DIMMs that, as you can see here, resemble or look like conventional DRAM DIMMs, but the main difference is that inside each of these DRAM chips, there are not only DRAM arrays, but also small processors called GPUs. Each of them can access their own DRAM bank, and they can enjoy like very high bandwidth that it's really suitable for memory-bound workloads. When I'm talking about a memory-bound workload, I mean that it's a workload that needs to access data very frequently while not performing much computation on this data. Okay, yeah, what are the key takeaways of this P&S? This P&S is aimed at improving your knowledge in computer architecture and in heterogeneous systems. We are talking about computer architectures, and we are talking about heterogeneous systems, and you have a bunch of materials that you need to study, or we recommend you to study, and can improve and enhance a lot your knowledge about these topics, computer architecture and heterogeneous systems. You will improve your technical skills in programming heterogeneous architectures. You may already have some programming experience in C and C++, which was a requirement of this P&S. If you even have some experience with parallel programming, that's going to be really useful as well. But in summary, you will learn much more in this P&S, either programming CPUs, GPUs, and FPGAs, and you will definitely improve your programming skills. You will also improve your critical thinking and analysis. And why is that? Because you are going to do research. In the end, the different projects that we are going to propose to you are related to our research. They may even be part of our own research, like, let's say, mini projects inside one of our bigger research projects, or they may be kind of follow-up projects after something that we have already worked on, or maybe we have even published. Or there are some ideas that we want to propose to you to follow up with these projects. And whenever you are doing research, for sure, it's critical to, so it's really important, it's really necessary to have critical thinking when you analyze whatever you are doing, whatever data you are obtaining or whatever, and being able to generate insights of the data and the results that you are analyzing. And you will also have a chance to interact with a nice group of researchers, which is our group. You will, well, you already know me, but you will know Gagan, Mohammed, and Exat pretty soon. You may also be in touch with some other researchers in our group, because we may eventually ask you to contact them as well, or may ask them to join some of our meetings if we want them to give you a specific feedback or something in particular that you're doing. And you will also get familiar with key research directions. As I said, you're going to do research with us. In some way, we are going to consider you part of our group during this semester. And hopefully, if you are excited, you will even continue working with us sometime later as well. And finally, you will also improve your skills as a presenter of technical work, because at the end of the semester, we will ask you to prepare a presentation about your project and present it in front of us and in front of other people from our group as well. In summary, the key goal of this P&S is to learn how to take advantage of existing heterogeneous devices by programming them, analyzing workloads, proposing offloading and scheduling techniques, etc. And the prerequisites, you already know them, but let me quickly remind them. You need to have a basic understanding of digital design and computer architecture, or this is a Professor Mutlu's course in computer science, but I'm pretty sure that you have taken, you may have, if not the same one, you may have taken an equivalent course. It's important and necessary to have some programming knowledge, especially C or C++. As I said before, if you have also some experience with FPGA or GPU programming, that's even better, because for sure you will more easily you will more easily beat the learning curve, so you will be productive much more earlier. But as I said, it's not strictly necessary, but desirable. And for sure, you need to have a big interest in what we are going to do here, learning about computer architectures and computing paradigm, discovering why things work or do not work when you're doing research, solving problems and developing your analysis skills and your critical thinking, and an interest as well in making systems, computing systems, more efficient and usable. This slide is about Professor Mutlu, who is the leader of our research group. He worked in Carnegie Mellon University until 2015. And then he joined ETH. In the beginning, he was in the computer science department, but now is in the electronic engineering department. He did his PhD in the UT Austin and has worked in several major companies like Google, VMware, Microsoft Research, Intel, AMD. Here you can see some, his website, the publications, and also his email address in case you want to contact him, and research. And his work is about research and teaching in computer architecture for sure, computer systems, hardware security, bioinformatics, etc. Many more things, as you can see. And these are the rest of the team of this P&S. I'm the lead supervisor, and I'm lucky to have other people on board like Dr. Alser, Dr. Salami, and Gagandeep Singh, who is a PhD student who will be graduating very, very soon. If you guys are in the meeting, maybe you want to quickly say hello. Mohammed?
Yes, hello everyone. Let me open the camera. Probably you can see me. Hi, it's me. Yeah, we will be in touch in the following days more, actually. Yeah.
Yeah, thank you, Mohammed. Yeah, actually, as you already know, we are going to present the project proposals next Tuesday, and Mohammed will have his own proposals, probably bioinformatics on FPGAs and GPUs, because that's his main topic of expertise. Bioinformatics is like I would say, the most skilled person in bioinformatics in our group. Exad.
Hello.
Are you there?
Yes, I'm here.
Hello.
Yeah, I don't know why this is Zoom, so I will try to turn off my video. Okay. So hello everyone, and thanks Juan. And I'm looking forward actually for the next week to discuss the project as well as the whole semester that we will be able to work together. So thanks a lot. Yeah.
Okay. Thank you, Exad. And Gagan, are you there?
Hello, Juan. Hello, everyone. I'm looking forward to working with you guys. And Juan already told you I'm a PhD student, and I'll graduate soon, actually. And yeah, so I'll be mostly working on the FPGA side. And if you guys are interested, I'll be really happy to work with you guys. Thank you.
Okay, thank you, Gagan. Yeah, it's only 4 of us. Many more people is in our group. This is the website of the group. If you want to check, other group members, research topics that we work on, recent publications, for example, and so on, and also our proposals for master and bachelor thesis that you may be interested in doing with us in the future. And this is a picture of the group. There, not even all researchers of the group are here. It's about 40 people at this point, very large group working on many different things. And yeah, as I said, you are somehow going to be part of this group during this semester, and we hope that you will enjoy working with us. And these are some of the current research focus areas in our group. Most important ones: computer architecture, hardware software co-design, and bioinformatics. But within these 3 big umbrellas, there are many more things like memory and storage systems, interconnects, heterogeneous and parallel systems, and GPUs, like the main topic of this P&S, system architecture interaction, energy efficiency, fault tolerance, genome sequencing, and many, many more things, as you can see in the slides. Yeah, what are the requirements and expectations of this P&S? For sure, attending is required for all the meetings. We are going to have, in principle, let's say the whole group is going to be today and next Tuesday. After that, we will assign you a project that is of your interest, and after that, you will have at least one weekly meeting with your supervisor or supervisors, and for sure we expect that you attend all of these meetings and make very good progress in your project and in your research. We also expect from you that you study the learning materials, even though there are required and recommended materials. For example, in this first meeting, for this first meeting, all of them are highly recommended. So we definitely encourage you to read them all, watch all the lectures that we have provided to you as well. Each of you, as you already know, will carry out your own hands-on project, and you will work in close engagement with your supervisors. And we also expect that you participate and ask questions and are willing to discuss thoughts and ideas, either with your supervisors directly or using the Moodle for Q&A forum. You can also, we can have some interesting discussions as well there. And for sure that you read the papers, because for now we have assigned to you some materials that are, let's say, good for everyone. I'd like the introductory to the whole P&S for all students, but after that, each of you will be assigned also more specific projects, more specific papers about the topic or the project that you are going to be working on. We will help a lot in all the projects, that's for sure. Not only your supervisor, but as I said, you may be eventually also get in touch with some other group members if we consider that they can help you in some particular aspect of your project. And the goal, because we are doing research, and our goal when we do research is to publish and contribute something new to the community. So if your work is really good, we may help you to get it published, or we may integrate your work into one of our projects and papers. So we hope that this is what will happen, and we hope that this also motivates you to do very good job. The course website, let me very quickly show it to you, but even though you may have already seen it. This is the course website. It's not only for this P&S, you can also see other P&S proposed by or offered by your group. Here you have course description, prerequisites, you have the contact information of us, and then scheduling. I will upload the slides here right after the meeting, and also the recording of this meeting as soon as it's ready. And then there are some materials required, recommended, and also some more for suggested for extension and learning even more. As you may see, not all of them are in the list that I provided to you over email, but that's fine. I mean, the good thing is that you have even more materials, and you have the chance to learn even more by reading these papers. And also here you have your homework 0, which essentially is like student information that we would like you provide to us. Some questions about you, exactly what are you studying, what semester, what are your expectations in this P&S, and so on. And you need to submit this assignment using the corresponding assignment in Moodle. As you can see, you all have access to this Moodle already. And here there are also some announcements. It's the first post that you see here has exactly the same contents that I sent to you over email. There is another announcement about the homework 0, about this student information that we want you provide to us. And finally, there is also a post about our digital design computer architecture course, a link to the schedule of the previous semester, and also some recommended lectures that we believe that are, I mean, if you want to somehow quickly brush up on these topics, they can be really help you, they can be really useful for, to you to have, let's say, like the basic knowledge of computer architecture that you need to take this course. Okay, let me go back to the slides. Yes. Yeah, website, Moodle, you have already seen this, and these are the materials that I provided to you over email. I put them all here in this slide for your quick reference. There are 2 lectures on SIMD processors and GPU, and then another lecture on programming GPUs that can be good as an introduction to heterogeneous systems. And then a little bit more about programming heterogeneous collaborative device systems, like one more lecture, and then 3 important papers of us. And finally, this one, which I also recommended to you in the other P&S, which is processing in DRAM with the UPMEM system that we also introduced a few slides ago. Our next meeting is next Tuesday at the same time. I hope you both attend, and also the other 2 students that we are missing today. In this meeting, we will announce and explain the projects that we are proposing to you. We will also give you the chance to select your favorite projects, and after that, also based on you know, what's your background, we will find what's the most suitable project with you. So we will find what's the most suitable project to you. We will assign it, and then you will have a supervisor who will start providing you with some materials that you need to study to start working on the project, and you will start having, as I said, at least 1 weekly meeting with your supervisor. And yeah, so that's more or less what I explained, individual meetings with your mentor or supervisor. We may eventually ask you to attend some other talks, maybe about GPU programming or FPGA programming, or maybe we can also provide you with some talks from Professor Mudlu, or presented in conferences about our published works. Yeah, we will see. This all will also depend on the specific project that you are carrying out. And finally, as I also said at some point during this presentation, you will have to present your work in front of us, your project, the progress that you made, what are the most interesting results and insights that you got. And we will expect that because you're going to be very successful in this P&S, you will tell us a lot of interesting new things. Okay, and that's all from my side, I guess. We still have a little bit of time if you want to ask any questions. If not, you can also reach me over email or in Moodle as well. Yeah, feel free to ask anything.
Maybe one question regarding the presentation. So we're expected to be done by the end of May, right?
So there is when the semester officially finishes. What we hope is that you will be motivated to I mean, imagine that you are developing your project and at some point you feel like, I don't know, with work, maybe working a few more days, few more hours, you can do something even bigger. We will be glad to continue give you support a few more weeks. And even if you are doing something really interesting and we think that it's something that, for example, we can publish, we will definitely encourage you to continue working with us until we complete the whole project. Eventually, I mean, essentially, this means that the more motivated you are to do good work and do good research with us, the more support you will get from us, and the longer you can have this experience. But yeah, essentially, the semester ends. I think it's in the first week of June, and that's what you officially have to take. But this, this will, as I said, depend on how motivated you are and how much good progress you are making as well. The final presentation will be sometime later. This is something that we will decide also based on our availability and based on your own availability as well, because after the semester finishes, maybe you take some holidays or maybe you have to prepare exams or whatever. So we will find a good date for everyone. So just for you to have as a reference, in the fall semester, we had the P&S on PIM, and the final presentation was on February 15th. This gave enough time to all students to do their exams, but also enough time to prepare their slides and discuss with the supervisors, get feedback on how to improve the slides, and then present them. So, but that's, as I said, it's just one day where you do the presentation, and we will find a suitable date for everyone.
Sure. Thank you.
Yeah, you're welcome. Okay. Any other question? Or maybe any other comment from you guys, Mohammed, Besat, Gagan?
All sounds good to me.
Okay. Yeah, thank you very much.